Okay, in the video here, we're going to look at the physical properties, nomenclature rules, and basic structural effects on stability for the alkene functional group. So recall that the alkene is a compound with a carbon-carbon double bond in it. Okay, I want to just review here some basic structural things that we've already covered in chapter 2, but let's just review them anyway. Okay, so a carbon-carbon double bond, remember, consists of a sigma bond and a pi bond. Okay, here's the sigma bond right here, and the pi bond is formed by overlapping these two p orbitals, which have to be parallel to each other to form the pi bond. Okay, an important thing to note here is that when we rotate around this carbon right here, okay, we don't do anything to the degree of overlap in the sigma bond, but we do some serious damage to the pi bond, okay? These are not parallel to each other anymore. We refer to this orientation here as orthogonal, meaning that they're 90 degrees, and the pi bond is essentially broken. So this is one big difference between alkenes and alkanes. You cannot rotate around the CC double bond like you can around the CC single bond. Okay, what does that mean for these two compounds here? Okay, if you look at this compound and this compound, hypothetically they could be interconverted by rotating around the carbon-carbon double bond, but since you can't do that, of course, they have to be different compounds, and we refer to them when they're on the same side, or on opposite sides rather, as being the trans alkene, and when they're on the same side we refer to them as the cis alkene. Okay, all right. Okay, so just remember this from chapter 1, that as you change the degree of bonding from a single bond to a double bond, the bond gets shorter and the bond gets stronger. Important thing to note here, though, is that the bond is not 2 times as strong, okay? And this is because the sigma bond is stronger than the pi bond, okay? 375, if you recall, if you multiply it by 2, is going to be 750. So 720 is less than 750. This shows that the second bond is not quite as strong as the first bond was. And if you go to a triple bond, these trends continue. Okay, so let's just look at the physical properties and the nomenclature rules first for alkenes. Alkenes also have the synonym name olefins. That's an older term, but you still see that a lot of people use it. Okay, so here's the basic rules. Everything we said about alkanes still applies as far as like numbering systems and names of substituents and rules like that, but we're going to change the rules a little for an alkene. Okay, so rule 1. We're going to have to find the longest chain, and the chain that we find has to include both of the alkene carbons. Okay, rule 2. We're going to number from the end that's going to give the first alkene carbon that we encounter the lowest number. And rule 3, we're going to symbol the name the same as we did for alkanes, except at the end of the name, instead of ane or ane, we're going to have -x-ene, where x is the number of the first alkene carbon. The second alkene carbon is assumed to be the number after the first alkene carbon. Okay? Alright, so even though an alkene is occurring over 2 carbons, only one number is going to be used to locate it. the position of the alkene. Let's name this compound. All right, so we're going to number the longest chain is the one right here. We're going to number from the right end because if we number from the right end, our first alkene carbon is at carbon 3. If we number from the left end, it's 1, 2, 3, 4, 5, 6, 7. We don't get our first alkene carbon until carbon 7. Never mind that we get some other branches a little quicker. Only the alkene counts when you're naming an alkene. Okay? All right. So what's the name of this compound? Its technical name after the rules changed in like 2004 is 8-chloro-7,7-difluoro-3-methyl-des-3-ene. An older rule would have you putting the 3 in front of the des, but either way is okay on your exam, but I think the top method is now considered the more acceptable way to do it. We're giving the position of chlorine and fluorine kind of high numbers, but that's because the alkene takes priority in the numbering system. Okay, here's some common names for alkene-containing groups. 2-carbon alkene group. It's just a vinyl group. You've heard the term vinyl before when you refer to plastic, right? We're going to see at the end of chapter 6 how that name really applies, okay? We're going to see that these vinyl derivatives actually are a precursor to a lot of materials that we collectively refer to as plastic. Okay, the 3-carbon group, where we have the direct attachment to the CH2 group and the double bond later, is referred to as the allyl group. We're going to see the significance of the allyl group much later in chapter 10, but these are the common names for those groups. Okay, and sometimes you'll refer to the position or a carbon directly as part of a double bond as being a vinylic carbon, and this carbon, one carbon away from a double bond, as being an allylic carbon or an allylic position. Okay, if it's cyclic, here's how we change the rules a little bit. Carbons 1 and 2 have to be alkene carbons. Carbon 1 should be a branch point. Okay. If there are no substituents on the alkene, we're going to choose C1 and C2 so that the first branch point has the lowest number. There's no number indicating the position of the alkene since C1 and C2 have to be the alkene carbons. Okay? Alright, if there's more than one alkene, you'd have to have a number, but we'll cover that in the chapter on dienes, chapter 10, or molecules with 2 or more alkene groups in them. Okay, rule 2 is that we assemble the name like acyclic alkenes. Don't forget the prefix cyclo. Okay, because of rule 1, we're going to see that these two compounds look very similar, but they're going to have actually quite different names. Okay. All right, so if we look at the rules applied to the compound on the left, of course, this has to be C1. Okay, and in this one right here, there's no preconceived notion as to what C1 and C2 is because neither carbon here has a substituent other than like the remainder of the ring. So we can choose either one of these as C1 or C2. Okay, so let's look at how we name these. This is the numbering system for the compound on the left. C1 is chosen for us because it's the branch point. That means the other alkene carbon has to be C2. Okay, we don't get to the methyl group until we get to C6 this way. Okay, our name for this compound is thus 1,6-dimethyl-cycloheptene. In the other compound, we have the choice as to which carbon is going to be carbon 1 or carbon 2. If we choose this carbon as carbon 1, which I've designated already as being carbon 1, what you can see is that we get to the branch point 1, 2, 3, 4 at carbon 4. If we choose this as 1, that means this has to be 2, 3, 4, 5, 6. We wouldn't get to the branch point till C6. Okay, so this compound thus becomes 4-methyl cycloheptene. Okay, let's look at some of the structural effects. First, I'll give you a problem here. Just name these two alkenes. Pause the video and name it yourself. Just see how your name uh, conforms or agrees with the one that we come up with here. Okay, then we're going to talk about how we classify alkenes based on their degree of substitution. Okay, so the name for the compound on the left is going to be named as a derivative of cyclohexene. It just becomes 4-ethyl, 4-methyl cyclohexene. Okay, we would choose this as carbon 1. Choosing this as carbon 1, 1, 2, 3, 4, 5. We wouldn't get to the branch point till C5. So 4-ethyl, 4-methyl cyclohexene would be the name. Okay, what's the name for the other one? Well, it's tempting to put this carbon here as carbon 1, but we don't do that because the alkene controls the numbering system here. So this becomes 666 trichloro 5-methyl 1-hexene. Okay, we have to number it this way. And remember, the 1 implies that C1 and C2 are alkene carbons. Okay. Now, another important nomenclature term for alkenes is that we classify them based on their degree of substitution. Okay, so we're going to assume in this that the molecule ethylene is the only truly unsubstituted alkene. Okay, and we refer to the degree of substitution of an alkene as to how many R groups there are on the alkene carbons compared to how many there are in ethylene, which has 0 substituents. Okay, so we have 6 basic substitution patterns for an alkene. We have monosubstituted, where we have 1 substituent on the alkene. If we have 2 substituents on the alkene, we can have them 3 different ways. They can be the trans 1,2 disubstituted, cis 1,2 disubstituted. Okay, we're calling this carbon 1 and 2. Or they can be 1,1 disubstituted. Okay, and the other 2 classifications are trisubstituted and tetrasubstituted. Okay, so we had sort of looked at the SIS Trans as being a good way to tell the difference between these two. Okay, but when you get to a trisubstituted, SIS Trans just doesn't work anymore. Okay, so this is now inadequate. So we refer to the SIS Trans nomenclature as being kind of like the common nomenclature system. It's good enough to talk to another person and tell what you're talking about, but it's not part of the official name. The official name is going to use E and Z to replace SIS and Trans. Okay, so to name something according to its EZ rules, we're going to have to go through a series of steps, and E is going to be stands for the German word entgegen, which means opposite, and Z stands for the word zusammen, which means the same. Okay, rule number 1. We're going to assign priority numbers based on the atom, not the group. Remember, it's just the atom that's directly attached to the alkene carbon. And we're going to rank the higher atomic weight as priority 1, and the other is going to be priority 2. These are called the Kohn-Ingold pre-log priority numbers. We're going to revisit them in Chapter 7, so it's important to remember the rules for how to assign them right here. Okay. So if we look at this molecule up in the upper right where we could not assign the cis and trans anymore, we can just look at the atoms that are directly attached and we can assign the priority numbers, right? Chlorine is heavier than hydrogen. A lot heavier, right? Ethyl, which means that we have a carbon directly attached, isn't quite as heavy as fluorine. Carbon has a molecular weight or atomic weight of 12, fluorine atomic weight of 19. Therefore, fluorine is heavier. Fluorine becomes number 1. Okay, if the number 1s are on the same side, it's going to be the Z isomer, and if they are on opposite sides, it's going to be the E isomer. Okay, so this compound, of course, is the E isomer, and its official IUPAC name would be E, 1-chloro, 2-fluoro, 1-butene. The official IUPAC name of the compound on the left would be E, 2-butene, and the IUPAC name for cis 2-butene would be cis 2-butene. Okay, these are, for lack of a better term, there's an obvious pun here. I'll just get it off the table right now. This one is easy. Easy. Get it? Okay, all right. Let's look at a more complicated situation. So these rules here we're going to see break down. We can't describe everything that we have to assign easy to with these two rules. So we have to add refinements. Refinement number 1. If you cannot reach a decision based on the atoms directly attached to the alkene, move one atom further away. And hopefully then you can find a difference. If you can't find a difference there, keep moving. Okay, you have to keep moving until you find a difference. What if you never find a difference? Well, that means that you don't have an alkene that's capable of having E and Z stereoisomers. Okay. It means it's symmetrical, and you wouldn't use the E and Z in that case. All right. So let's look at this one. Okay, sorry, before we look at these, let's add refinement number 2. Pretend that multiple bonds are an equal number of single bonds. So let's look at the first one. All right, so bond line formula has eliminated this hydrogen, but it's still there. We can probably see quite clearly that methyl is going, or carbon is going to be heavier than hydrogen. Okay, what about here? There's a carbon. There's a carbon. These two look a lot alike, right? We can't make a decision right there. We've got to go further out. So let's go one atom further out. We'll just call this A and A prime, B and B prime. All right, we're still not able to make a decision, right? We've still got carbons. All right, let's go further. Now we got a difference here, okay? Here, this carbon here has an oxygen on it. This carbon, which is the same distance from the alkene, does not have an oxygen on it. Therefore, this side becomes priority 1. Okay, and I think that I already have that there. Yeah, so the right side of the second carbon becomes priority 1. And the other side here becomes priority 2. Okay? I'll put the answers down in a second, but we can see pretty obviously that the number 1s are on the opposite side of the alkene. That's E. Okay. What about the other one? Well, the other one, we have a little bit of a complication. And that's the cyanide. Cyanide, remember, is a carbon-nitrogen triple bond. Okay, so we got a multiple bond. This is also has a classic trick question in it. You'll see it. It's not really a trick question, but some students interpret it that way. Okay, so we're going to pretend that this nitrile is 3 equivalent carbon-nitrogen bonds. Okay, if we look over here, on the left side, fluorine is heavier than carbon. So the fluorine gets number 1, the other carbon gets number 2. I think a lot of people are probably tempted to call this side number 1. Because iodines are quite heavy, but remember, it's the atom, not the group. So the fact that this is just carbon competing with fluorine, okay, and fluorine is winning. On the other side, we have carbon directly attached in both substituents in the top and bottom, but the one on the bottom has 3 nitrogens attached to that carbon. Technically, the other carbon only has 1 nitrogen, so the bottom carbon is going to be number 1, and this is going to be number 2, and thus this becomes the Z isomer. Okay. All right, so let's do a few problems here. Assign the proper E and Z designation to each alkene. You should pause the video, do it, then restart it when you're done. Okay, so the one on the left is an extremely easy one because you can just look at the atoms attached to the alkene and come away with a decision right away. Okay? All right, so the priority numbers for this one are easy to assign. This next one, you're probably saying C600H12O1. Aren't there an awful lot of isomers for that compound? Well, yeah, you're absolutely right there. But you don't have to worry about that because what it's competing with has an oxygen on it. So because of that, it will beat every single isomer of C600H12O1. Okay. And on the other side, we have chlorine competing with CBr3. Remember, since there's a carbon between the bromines, chlorine is actually going to be number 1 on that side because chlorine beats carbon. Okay? In the other one, we have a multiple bond. The left carbon isn't too difficult to assign the priority numbers to, right? Number 1 and number 2. But the right carbon, we have to convert the multiple bond to an equal number of single bonds. Thus, we assigned priority to the top side of the alkene, or priority 1 to the top side of the alkene, because there's 2 oxygens over there versus 1 oxygen in the same location on the bottom face, or on the bottom side of the alkene. Okay, so this is E for the left one, Z for the middle one, and Z for the one on the right. Okay. All right, let's look at the effects of structure on relative stability. Okay, so we're going to compare isomeric compounds formula C4H8. Okay? All right, so all of these react with 6 oxygens to make 4 CO2s and 4 waters. And we look at this on a potential energy diagram here. So this is increasing energy on the y-axis, remember. What we see is that the higher heat of combustion one, which is the monosubstituted alkene at 2717 kilojoules per mole, is higher in energy than the cis alkene, which is higher in energy than the trans 2-butene or trans 1,2 disubstituted alkene. Okay, down here, recall that they're all producing the same products upon combustion, right? So the energy of the products is the same. The only difference here is the energy difference of the reactants. Okay, so this is an important thing to remember, that the more substituted alkene is the more stable alkene, or the one that's lower in energy. And the other issue, this is a little bit less important, but it's also important to remember that this is happening as well, is that the cis isomer is usually less stable than the trans isomer. Okay, so in the cis isomer, we have a little bit of a steric interaction right there. Technically, they're eclipsed. That would look kind of severe, but remember that the bond angles are 120 degrees, so they're a little bit further away from each other than in this awful compound from chapter 3, the fully eclipsed isomer or conformation of butane. Okay, so they're pulled back a little, so they're not quite as bad as fully eclipsed butane, but the cis isomer is usually generally a little bit less stable than the trans isomer because of the steric effect. Okay. All right, last one here. We have cyclobutane, of course. And we see that its heat of combustion is a little bit higher than all of these, but we made a big deal about angle strain, right? But it's really not terribly different from all of these. So what gives here? Well, the deal is that a sigma bond is generally stronger than a pi bond. So all the bonds in cyclobutane are sigma bonds. And the only reason it's close is because of angle strain. If it wasn't for the angle strain, we would see that cyclobutane would probably be much more stable than these compounds here. Okay? All right, so take-home lesson are these two statements here, that the more substituted alkene is the more stable one, and that cis is destabilized relative to trans due to a steric effect. Okay, let's look at some additional structural effects on alkene stability. All right, so angle strain becomes a lot more severe if we put sp2 carbons in the ring. This is because sp2 carbons want 120-degree bond angles, okay? And these small bond angles that we see in cyclobutane and cyclopropane are a lot further away from 120 degrees than they are from 109.5. Okay, so the degree of angle strain becomes more severe when you put a double bond into a small ring, or when you make one of the carbons in a small ring an sp2 carbon. All right, we can see that in the heat of in the delta H's for these transformations right here. Okay, normally a tri-substituted alkene is more stable than a monosubstituted alkene. Yet this process, converting the tri-substituted to the monosubstituted, is actually quite exothermic. And this is because we have rather severe angle strain. Okay. As we make the ring larger, this severe angle strain goes away. Okay, so in this next example, the tri-substituted double bond in the 4-membered ring going out here, it's less exothermic. When we get to the 5 and 6-membered rings, it's exactly what you expect. The tri-substituted double bond compound is more stable. Okay. All right. So because of this severe distortion of the bond angles, we don't want to locate sp2 carbons in small rings. The other structural effect worth noting is that we cannot have the trans configuration for cycloalkenes in small rings, okay? All right, so if we look at cyclohexene, which we've written lots of times in this class, it's very obviously a cis alkene, right? If you can force it to be a trans alkene, we'll put the hydrogens here so it looks more trans-like. It's actually too unstable to isolate. It's never been made. It's a very high energy compound. It's not till you get to an 8-membered ring where you can actually isolate the trans isomer. So trans cyclooctene, shown here on the left, is much less stable than cis cyclooctene. Okay, but we noticed previously that we said that cis wasn't as stable as trans, but we're having an exception to the rules here, and this is really because these two carbons are quite far apart. So it takes a lot of carbons to link them up. Okay, so when we get to an 8-membered ring, we have a compound that's kind of unstable, but we can still isolate it. When you get to a 12-membered ring, that's the first ring that you have where the trans isomer actually becomes more stable than the cis isomer, like you would expect. That's the same rule that you see with a non-cyclic compound. Okay, when we have a bicyclic system, like you see in this compound right here, it's very difficult to isolate these when the double bond is at the bridgehead. We call this type of an alkene an anti-Brett olefin or an anti-Brett alkene. This particular alkene, if we count here, is basically like an alkene in a 7-member or transalkene in a 7-membered ring. This we're going to say is the inside substituent, and this one has to be the outside substituent or cis to hydrogen, right? Okay, so if this is cis to hydrogen, this means that this is essentially a transalkene in a 7-membered ring, and that's too stable to exist. Remember, the smallest trans cycloalkene that you can have is trans cyclooctene. I can say that when I took organic chemistry, it was hard to visualize trans cyclooctene. But then an electronic game, Pac-Man, came onto the scene. And this is widely referred to as the Pac-Man form. And this is the stop sign form. Okay, so that's a good way to remember these two. Okay. All right, we're going to end this video with a problem here. You should pause it and go ahead and do the problem, but this is an important type of problem. Rank the following compounds as to their relative stability. Put the most stable one, or the lowest heat of combustion, as number 1, and the least stable one as number 5. Hint, If it can't exist, rank it as number 5. All right, right away, there's one here that can't exist at all. And this is the compound that has a trans alkene and a 6-membered ring. That's number 5. Okay. The other issue is that these two compounds here have sp2 carbons in small rings. Okay, this has two sp2 carbons in a small ring. This has one sp2 carbon in a small ring. Okay. And the other two, first two, the double bond is not in the ring at all, so we don't have to worry about those. We just count up the number of substituents on the alkene to rank these two on the left. Okay, so the final ranking would have that one over there. The tri-substituted alkene is number 1. The mono-substituted alkene, free of any carbons in small rings, is number 2. Then the 3 and 4 would be we would rank these due to the number of carbons that they have in the small rings. And the least stable one would be the trans cycloalkene, which, again, has no capability of existence at room temperature. Okay, all right, so this is where we're going to end this video right here.